Hi everyone. In this video, we're going to talk about linear and exponential functions. Now, I think it's important to teach these functions at the same time, so that way it makes it easier for us to compare and contrast the various attributes of these functions. It's always easier to learn something in comparison to other things so that you really understand what it is that you're learning. For example, if you were trying to understand the concept of color and you were only shown the color red, it would be really tough to understand the idea of color. So instead, when we learn colors, usually we learn several colors at the same time, such as red, blue, green. I mention this because my 1-year-old son is starting to pick up on different colors. He's actually 1.5 now, but he's starting to understand the difference between blue and red. It's because I show him a bunch of things that are all blue and a bunch of things that are all red. And so that's what I'm attempting to do here, is to help us understand the idea of functions in general by studying two specific functions at the same time. And so we're going to keep studying lines and exponential functions in different ways throughout this whole unit. Okay, so I wrote the general form of a line that I tend to use. There are other forms, as you have seen in prior videos, but I tend to use mx plus b or b plus mx. So it can be written either way because addition is commutative. I also wrote the general form of basic exponential functions. So exponential functions can get more complicated looking than that. They can be translated and shifted and other things that we're not going to discuss in this course. So this is just the most basic structure for an exponential function. And then I gave us some examples here. So I want you to pause your video now and see if you can find the y-intercept and the rate of change, or the slope, of both of these functions. So this is a linear function, this is an exponential function. So pause your video and try that now. Okay, let me see if I can do this in some different colors. So for the linear function, this is not written in a way that allows me to see what the slope is. So if you were thinking that the slope is 3 because it's multiplying by the x, that's not right, because this is not yet solved for y. It doesn't look like this form. So the first thing that you have to do is you have to manipulate this using legal actions in algebra to make this an equivalent equation that says y equals. So to get this to look like y equals, we have to subtract 3x from both sides. That will leave us with 10y equals negative 2 minus 3x. And then we have to divide both sides by 10. So divide both sides by 10, you will get negative 2 over 10, and then negative 3 over 10 times x. I'm just going to leave them as fractions. You could write them as decimals if you want, but if you're looking for an exact answer and you don't want to approximate it, then fractions are fine. So the slope, you can see it's right here. The slope, or the rate of change, it means the same thing, is negative 3/10. Always the slope is what's written, just the number. It's not 3/10 times x. It's not that full thing. So the slope, you're telling me how fast the function is changing, and that's just a number, right? If I asked you how fast do you drive, you wouldn't say you drive 60 miles per hour x. You would just say 60 miles per hour. So the slope is always just the number. The y-intercept of a linear function is the constant that's just here adding or subtracting. It's the thing that doesn't have an x. So the y-intercept for this specific example is negative 2/10. Or if you wanted, you could reduce that to negative 1/5. It's the same. Okay, so that was for the linear function. So now let's look at the exponential function. This one is a little bit different. You don't have to solve for y because it's already written in terms of y equals for you, so that's nice. But there's still some work to do. So the y-intercept, let me write this in blue so it doesn't clash with the pink color so that you can see it. I'll bring my camera a little closer. So the y-intercept is the a value in this general structure It's the a value. It's the number that's being multiplied on the outside of this exponent. So it's just 3 in this case. And then if you want to know the rate of change, I like to do that by thinking about the factor here. This is called the factor, or the b value, the factor, or the base. I like to picture that as a percentage because the rate of change in exponential functions is always a percent. It's a percent change. In linear functions, it's a constant amount. You know, like if this represented dollars, it would be the same dollar amount that you are adding or subtracting every time. But with exponential functions, such as when you have a bank account and you're compounding interest, you don't add the same dollar amount every time. You're taking a percent of a new amount, and then when you get that new answer, you take the same percentage of that new answer, which will give you a different amount. And then you keep, so your answer keeps changing, even though the percentage is the same, because you're taking a percent of a different amount. So if you think about this 1.6 as a percentage, if the factor is 1.6, which is the same thing as 160%, I did that by multiplying by 100 here to get that as a percent. Then that means the rate of change, which is the same thing, same idea as the slope, is 60%. How do I know that? Because 160 minus 100, because you always start with 100, gives me 60%. So in other words, if this were a function modeling some real life problem, then whatever the y value is measuring, whether it's dollars or students or inches, whatever it is that it's measuring, that is increasing by 60% every x value, whatever the x value is, whether it's time in minutes or years or whatever it is. Every one x unit, the y values are increasing by 60%. So that's what the rate means. I can show you a picture of that down here and then I'll erase it, but this might help. So if you go back to our lessons on percents, you'll see that the factor that you see in the actual equation represents the final percentage. It's this whole, maybe I should write this outside of here. It's this whole box. This is 160%. And you always start with 100%. As you know, you always start with 100%. So if you keep landing at 160%, so the way you find your new y value as x increases by 1 is you multiply by 160%. That means your new amount has increased to 160%. I'm going to bring back the by and the 2. So if you've increased to 160%, what did you just add on? What you must have added on 60%, which means you increased by 60%. So there's the by and the 2 coming back at us from earlier lessons, which is good because it helps us to confirm our knowledge and shows that what we learned previously is useful for some of these real life ideas about functions. Okay, now this percent business, that's only necessary for exponential functions. You never have to do percents with linear functions. It's that linear functions change by a constant amount. Exponential functions have a percent change. Okay, so now we're going to look at 2 word problems, each showing us these 2 functions. So the first one says, the function h of t equals 80 minus 32t models the height in feet of a rock after t seconds. This is a linear example. And then this other example says the function v of t equals 3 times 1.4 to the t models the value of a mint condition toy after t years. Okay, so you can see that these are 2 different ideas. Let me move this so I can kind of bring this in. One is talking about the height of a rock, and then the other is talking about the value of some toy. So this function is a line. How do I know that? Because I can see it looks like y equals b plus mx. That's what it looks like to me. So let's say that you were asked to find the slope of this function and interpret what that means in layman's terms, in non-mathematical sounding jargony terms. Can you explain it to somebody who dislikes math, who, has anxiety about math and doesn't want to hear mathematical terms? Can you explain what the slope means in layman's terms? So pause your video now, see if you can find the slope of this function, and then also interpret what it means in the context of this function. Like, what is this rock doing, in other words? I'm going to rewrite the function down here underneath this so that we can see. Okay, and I'm going to go ahead and interpret the slope. So first, I see that the slope is negative 32. Remember, it's only the numerical value, and it has to also come with the sign, the plus or minus sign. And it never has the variable, so don't put a t there. That would not be correct. Let me see if I can turn off that light that is causing a glare. Okay, that's better. All right, so now we know that that's our slope. Now we have to interpret it in terms of the context of this problem. So what does that mean? Well, the slope, always the definition of slope is as x increases by 1, and it doesn't have to be x, it's whatever the independent variable is. As x increases by 1, how does y change? Some people internalize that as rise over run, which means you're thinking about what the y values are doing over the x values, which will help you get x down to 1 unit. That's why you're dividing. So what this means is if you know what the y value is being measured in, which in this case it's being measured in feet, and the x value, or the independent variable, the t variable, is being measured in seconds, this must mean that the rock is falling because we got a negative sign, is falling 32 feet every second, or per second. You could say per second, or you could say every second, or you could say each second. All of those mean the same thing. So when you're interpreting a slope, it's really important to use those keywords per or every, because that's how you include this idea of x increasing by 1. You're saying, here's what y is doing with every 1 second increase, that's what it means to have as x increases by 1 unit. In this case, x represents seconds. It represents the time. So this must mean the rock is falling 32 feet per second. That's what the slope means. If you were interested in the y-intercept, like maybe you were asked to find the y-intercept of this function, try that now. Pause your video. What is the y-intercept? And what does it mean in the context of this problem? Okay, so I have not as much room. I didn't plan on asking us that, but it's good to round out our knowledge. So let me erase this every here, and I'll just put it underneath. I'll bring this down so you can see. The y-intercept, or the vertical intercept, they mean the same thing. The y-intercept is 80. I can see it right here. There's the y-intercept. I could put b equals 80, so you can see it. And what does this mean? The rock was initially 80 feet. Initially 80 feet high. You could say it like that. Okay, so the key words when you're interpreting a y-intercept is that it's the starting amount, or the initial amount, or the beginning amount. Something that you're signaling to us that it's the start. The keywords with slope is the idea of per, or every. It's happening every x unit, whatever your independent variable, whatever the units are of the independent variable. So let's try a problem with the exponential function now. So those are the two things about linear functions, the two most important attributes of lines. That's why you see those variables inside this structure, is understanding the slope and then also understanding the y-intercept. So now with exponential functions, the two most important things to understand is the y-intercept, the starting amount, and the factor, and how you can use that to find the rate of change. Okay, so let's go ahead and start by finding the rate of change of this function. and interpret what that means. Okay, so generally exponential functions look like this, where b is your rate or your factor. You use it to find your rate. It's not your rate. B is your factor. Okay, and so this looks just like that, where I can see b is 1.4. And if you want that as a percentage, just multiply by 100. So you'll get 140%. So if your factor is 140%, then what is your rate? Well, if your factor is 140, and I draw that picture, this whole thing is 140%. You always start at 100%. Then what must you have just added on to 100 to get us to 140%? It must be 40. So let's put that here. You must have just added on 40%. That's what's in green right there. So that's your rate. So the rate is 40%. And what does that mean in the context of this problem, which is modeling the value of a toy after t years? It means that the value of the toy increases because this is more than 100%. 1.4 is higher than 1, so you're increasing. That's a growing function. So the value of the toy is increasing by 40% each year or every year. And the key word is making sure you are getting the every one x unit, just like we did here. It's the same thing. As x increases by 1, how does y change? But for exponential functions, we're talking about how does y change in terms of a percent. So two key features. You should have a percent symbol when you interpret the rate of change of any exponential function. And you should have this concept of each or every or per, however you want to say that. They all mean the same thing. So that's the rate. And then the final question that we could ask here is, what is the y-intercept and what does it mean? So go ahead and pause your video and try that last question now. Okay, so I'll bring this in so you can see. So here's your function, y equals 3 times 1.4 to the t. I can see the y-intercept is right there. It's 3. So I can say the y-intercept is 3. And if I'm explaining what that means, this means the toy was initially $3. And again, the key word there is making sure you're saying it's the initial amount or the starting amount. You're getting at that idea that it's the thing you're starting with. Okay, so now we've covered a couple real world examples that involve linear functions and exponential functions. You should see this kind of a pattern come up in your everyday life if you're looking for it. If you are really enjoying these lessons, it'll come up without you even realizing it. But when you're doing something at a constant rate, you're doing a linear function. So let's say you jog. If you jog at a constant rate, I jog pretty slowly, but I love running and being outside. But so let's say you jog at 4 miles per hour, then if you're doing that steadily, then your distance can be modeled by a linear function. Now, if you're doing sprints and then slowing doing like I've done some sprint workouts, then that wouldn't be a linear function anymore. That wouldn't even be an exponential function. That would be a crazy looking function where your speed is changing at different points in time. I happen to eat 2 eggs a day, right? So that would also be a linear function because I'm eating the same amount of eggs every day. So I'm doing something on a constant rate of change. Exponential functions can come up in our everyday lives, thinking about things that are changing exponentially. They have a radical increase or a rapid decrease that would most likely be modeled by an exponential function. For example, during the pandemic, any virus spreads exponentially, right? As soon as one person catches a cold, that person can spread it to 3 other people, and then those 3 people spread it to each 3 other people. So now we're already at 27 people, right? So that's spreading exponentially. So colds and viruses and things, they spread exponentially. So you'll see these concepts, they come up in our everyday lives without us thinking about the nitty gritty details here. But it does help to have a rough idea of how you can figure out how fast something is changing when you have a linear function, or how fast something is changing when you have an exponential function. And then you can make decisions in your everyday life if you have a good understanding of these rates. In our next video, we're going to cover more about lines and exponential functions, but I'm going to go more in depth about looking at tables. So now you have seen equations, you've seen word problems. We did some graphs in the prior video, and we also did some tables in the prior video, but I want to get more into depth with looking at tables and how you can tell looking at a table of values if the function is linear or exponential or neither.